No, this just goes to here, so I need this microphone as well. Yeah, okay. So if you would like, I could talk about Pythagoras and the false story of the Pythagoreans. You would like me to talk about the beauty of mathematics, and I would say you ought to talk to the professor of mathematics, because he will tell you the first thing about mathematicians is that we do mathematics because of its beauty, and the thing that drives most mathematicians to do mathematics is because mathematics is beautiful. But I'm not going to be able to show you that beauty. I can't have you experience that beauty unless you've done school mathematics and you're doing university level mathematics. And it's one of the great tragedies that children always think mathematics, at school, mathematics is so boring, which it is at school. It is boring. And when you were at school, did you like mathematics? No, you did. Okay, well that's unusual. Most people who are not. Sorry?
I said goodbye to math once I finished the school certificate.
Right. So you just left it. But the problem is most children find mathematics excruciatingly boring, and they hate it. I mean, the conversation I have all the time as I meet people, they say, "Well, what do you do?" "I'm a mathematician," and the reply is always, "Oh, that was my worst subject at school. I hated maths," and then they turn around and walk away from me, because everyone, is frightened of or dislikes mathematics or thinks that I'm going to want to talk to them about mathematics. And indeed, it's one of the fun things that people don't know what mathematicians do. They think actually what we do is we make bigger and bigger sums, or we do bigger and bigger multiplications and bigger divisions. And sometimes when you deal with people who don't know this, it's just easier to say, yes, that's right. Well, we just do bigger long division, just more long division. That's fine, that's what it is. Because trying to explain to them what mathematicians do is impossible. The problem is always that what you learn at school is to real mathematics the way spelling is to poetry. It's very handy to be able to spell so you can read and write poetry, but spelling has nothing to do with poetry. Poetry is a higher use of language, and what you learn at school is basically spelling. It is just the tools that you need to construct words, to construct sentences in mathematics. And then in mathematics, it's a university level mathematics, you start to talk about something else. And only at university do you do enough mathematics at a high enough level that you begin to experience, you begin to witness or perceive the beauty of mathematics. And it's a drug. And if most governments knew what kind of drug it was, most governments would forbid it, because like heroin or cocaine or something, it's an addictive drug. And most mathematicians do mathematics because they are addicted to this drug. And we reel students in, and we give them this drug, and then they too become addicted to this drug, because it is an experience, a unique experience of extraordinary power. Mathematicians all look at each other and know what we're talking about, and it's very hard to explain it to other people. I would come back to what Bertrand Russell wrote when later in his life, in his autobiography, he writes that he's been very lucky because he has had in his life the two experiences of sex and mathematics, which are two forms of ecstasy in which we can experience the vision of the saints. And I think most mathematicians would probably say, yeah, sex, mathematics, if I had to choose between the two, that's difficult. I'm not sure how most mathematicians would choose. I mean, many might choose sex, and many might choose mathematics, because it actually does give rise to a form of ecstasy, to an aesthetic experience, which is one where, yes, one does have some vision of the saints. And it is because you can think about things in mathematics which you cannot think about in ordinary terms. I used this example with somebody. Oh, thank you very much. I used this example with somebody yesterday you all know about tying knots, and a shoelace is essentially a two-dimensional line, flexible line, in 3 dimensions. What we live in, usually we call it 3 dimensions. Actually, we live in 4, but as well, don't worry, think of it as 3 dimensions. So tying a knot is taking a 2-dimensional line and tying it around itself in 3 dimensions. Well, okay, why stop there? Let's think about a 4-dimensional line in, let's say, 9-dimensional space. Well, that 4-dimensional line you can tie in knots. Only I can't draw it for you because I can't draw. Well, I can draw 3 dimensions. There's 3 dimensions: the x, the y, the z axes, and if I move it, you could say it is 3 dimensions moving through 4. And that's kind of a model of 4 dimensions. It's not very good, but it's kind of 4 dimensions. But if I talk about 5 dimensions, or 7 or 9 dimensions, or 29 dimensions, I have no way of showing you a drawing. So it is only going to happen in your head. So when you understand it, it's only going to happen in your head. And it's very hard to explain further to you until you've done enough algebraic geometry that you can start to think about multidimensional surfaces and multidimensional spaces and all that sort of thing. And now I've lost you. And that's why so few people understand the beauty of mathematics, is because you have to have so much more mathematical knowledge to understand it. So, your first question to me, which was, I've come here because I want to know about the beauty of mathematics, I genuinely can't answer you. I would take a different approach, which is to say, and this is why I would argue that mathematics is a language, because what language does is provide a symbolic system for us. I mean, it sounds. If I say the word cat, you immediately are thinking of, the furry creature that's sitting on a mat by the door. So I say a symbol, the sound cat, and you immediately interpret that symbol as the furry creature sitting on the mat by the door. Sorry. And you know how to decode that symbol. And so language, ordinary language, just uses a series of codes that symbolize phenomena that we experience, emotional phenomena or physical experience. It simply encodes experiences that we have and allows us to describe those experiences. And mathematics does the same. Mathematics enables us to encode mathematical experiences and to talk about structures and things, like, for example, a knot what did I say? It was a 5-dimensional string in a 9-dimensional space. I can describe those knots using mathematics. Those are experiences I can't give you in the physical world. I can't draw or construct in the physical world 5 dimensions or 9 dimensions, but I can talk about it in mathematics, and therefore you can, if you know enough mathematics, you can experience it. And just as ordinary English or Bengali allows you to convey something about your experiences or somebody else's experiences, so in mathematics it is a language which allows you to convey experiences. What's difficult is that mathematics is a cult-like language, because only a very small group of adepts to the cult can speak the language. So almost all of you are excluded from that language. But then if you think about it, one of the things tribes, communities always do is construct languages that define who is a member of a community and who is excluded from the community. That's one of the first things a language does. That's why doctors are incomprehensible except to doctors, and lawyers are incomprehensible except to lawyers, because they have a special language that they use, which is a method of demarcation. And mathematicians are perhaps the best of all at making this kind of demarcation and saying, no, you don't speak my language, you can't enter here, you're not a mathematician. And one thing, I do as a joke, is I will say of somebody, yeah, he doesn't know anything about this, he can't integrate over a sphere. And everybody who knows mathematics knows immediately, okay, I know what integrating over a sphere means, and if somebody can't integrate over a sphere, they have a certain level of knowledge, and if they can integrate over a sphere, they do have a certain level of knowledge, and it's a phrase which is exactly a demarcation that you probably have no idea what a integrating over a sphere is. And aside from you, sir, because you're a mathematician, who else here who knows what integrating over a sphere is? Nobody? Are you the only one who knows what integrating a sphere is? Are there no physicists here? Well, you know what integrating over a sphere is. The physicists will know what that means, because they do integrate over spheres regularly, but otherwise nobody knows what I'm saying. So it is a term which precisely demarcates mathematicians from non-mathematicians. And we use that as communities use that kind of thing in any circumstances to differentiate communities. So mathematics is also used, the language of mathematics is used in that social sense of creating communities and dividing communities. And, I say if it walks like a language, if it talks like a language, if it has feathers like a language, guess what? It's a language. The difference is you can't write a novel in mathematics. To which I then wonder, well, can you tell a narrative in mathematics? Maybe not a novel, because a novel you would want to have boy meets girl, boy breaks up with girl, boy meets up with girl's sister. I don't know. There's a story about some conflict or love or something like that, which then has a resolution, whatever it is, however that works. But there is a narrative that involves, say, conflict and emotions. Well, mathematics isn't terribly good at talking about conflict or emotions, but when mathematicians study an abstract structure, they will look at elements of the structure and then look at more elements of the structure, and eventually they with any luck will have a series of theorems that explain the whole structure. And this is rather like a geographer or a traveller exploring geography, because mathematicians literally find out what there is and what it looks like and how it relates to other things. And if you imagine the diary of an explorer studying geography, that is exactly what mathematicians do. So you might not be able to write a love story with mathematics, but you explore abstract parts of the world. The problem is always that it's abstract. And the problem is always, almost all mathematicians are Platonists. Now, what I mean by that is, again, do I need to explain Plato? Do you know Platonic philosophy? I don't want to explain what you already know. I know you know Platonic philosophy, but what about the rest? You don't know. Okay, but Plato has one of Plato's fundamental doctrines is that there exist two kinds of reality. There is this changing world, and there exists another kind of physical reality. Another kind of reality which is non-physical, which is unchanging and perfect and timeless. And he gives as evidence of this, if you look around the room, you're wearing green, you're wearing green. Is anybody else wearing green? Is there you two who are wearing? Okay, let's go for blue. Your notebook is blue. Your bag has some blue. Do you have some blue in your shirt? You've got a blue wallet. I can see sort of a blue shirt. Madam, I think you're wearing some blue. Your shirt is blue. Your shirt is kind of blue. My shirt is kind of blue. Do you notice, I mean, nobody has any trouble looking around the room and recognizing blue. And you know, the lid of my water is blue. So we all recognize blue really easily. But if you look at it, the lid of my water and my shirt are actually quite different colors. But you had no trouble recognizing them to be blue, and you certainly wouldn't mistake my shirt for a cat, or for green, or red, or whatever. But how did you know it was blue? Well, Plato's argument is that we have some knowledge of, some idea of a perfect blue, which is not an individual blue, but is, if you will, something like the definition of blue. Yeah, something like the definition of blue. He doesn't use those words. Plato doesn't use those words. Sorry, but he has this idea. He says you have some idea of blueness, and therefore you recognize that this in some way partakes in the quality of blue, and this partakes in the quality of blue, whereas, I don't know, this does not partake in the quality of blue. So he says you have this knowledge of blueness, but blueness doesn't change with time. Blueness never becomes something else. Blueness doesn't change with time. Blueness is a perfect, unchanging definition. Now, if Plato were in the room at the back, he would be standing up, waving his hand, saying that's a really bad definition of what I meant. Because the explanation Plato would like to give you for what we mean by this other kind of reality, this other sort of existence, is he would say, let's think of a triangle. Let's draw a triangle on the blackboard. So you go up, you draw a triangle on the blackboard, and then you draw a line parallel to the base of the triangle going through the apex of the triangle. I was going to draw it on the board, but you can think this one through. So I've got a triangle, and I've got a line going through the apex, which is the same as the base of the triangle. Now, when I draw that triangle on the board, you look at that triangle, and you should realize right away it's not a triangle, because what I've put on the board will be hand-drawn lines, which are not straight, which cross at great big thick blobs. A line is supposed to have no thickness, no parts, and it should cross at a point. So that the lines are not straight, they're not lines. They don't meet at points, so they're not lines. And indeed, if you tried to look where two lines meet, you would see that you couldn't measure an angle because the lines are bendy. So you've no idea where they actually meet. So Plato would say, what you've drawn on the board is not a triangle. But I can use that triangle that I've drawn on the board to notice that angles are the same, certain angles are the same, and I can use that triangle to show you that the sum of the internal angles of a triangle is the same as the angle of a straight line. You should remember that from school. Okay, you were taught that at school, trust me. You were taught that at school, and you should remember that the sum of internal angles of a triangle is the angle of the straight line. It's 180 degrees. I think every single one of you is going to answer your phone before this lecture is over. So, how did you come to that reasoning? How did you get this idea that the sum of internal angles is the angle of the straight line? You certainly didn't learn it off that triangle that I put on the board, because what I put on the board are not straight lines, they don't cross at points, you can't measure their angles. The line through the apex is certainly not the same as the parallel to the line of the base. It bears no relationship to a triangle. And Plato says that's because you're using this diagram as a crutch to think about a triangle, to think about an unchanging and perfect triangle. Now, Plato is actually quite subtle here, because he says the triangle in your head still exists in the changing world, because, as it were, I can nod my head and the triangle that I'm thinking about moves because my head is moving. And I and my mind come into being and pass out of being, so the triangle in my mind is not unchanging. I think about it, and then after I die, it ceases to exist. So the triangle in my head must have some relationship to something external to your head. And this is where Plato argues to what he calls, or what we call, I should say, his theory of forms, where he says that the properties of the world around us are manifestations of properties of another kind of unchanging, perfect, timeless reality, which is not physical. And Plato's argument is the best way to learn what he means by these unchanging ideals or unchanging forms is to study mathematics. Indeed, Plato actually describes, he explains what would be a good school, the way to teach people how to be good citizens. And you would start off with, the ordinary things like reading and writing and dance and whatever, language, grammar. And then you go to university and you study mathematics. And only when you've understood mathematics can you then go on to kind of graduate school, where you would learn other disciplines. But in order to know the world, you first must know you must understand mathematics, because only by understanding mathematics can you gain true and certain knowledge of the world. That happens to be a world-changing idea, because this idea you can only know about the world by studying mathematics is something that all mathematicians, and indeed physicists and so on, know, that you study the world through mathematics. But what it means and why you mean it and its significance, well, I'll talk about that in a bit when I talk about what happens in the Renaissance. But this idea that mathematics is a way of studying the world is an unbelievably clever innovation on Plato's part. But the core of Plato's thinking here is this ontological dualism, that there are two kinds of reality. There's the changing world that Plato calls becoming, and there is the unchanging world that Plato calls being. And these are two kinds of reality. They're both perfectly real, but they have different properties, and we know about them in different ways. Now, almost all mathematicians are Platonists, and almost all mathematicians, if you ask them, they will give you. You ask them, what are you studying? What are the objects of mathematics that you study? They will usually try to avoid this argument because they're frightened you're a philosopher. So they don't like to talk to philosophers. So they'll try and avoid it. They'll try and leave. But eventually, if you're lucky, the mathematician, you can get the mathematicians to explain what they mean by the objects of mathematics, and they will generally come back to the idea that they're Platonists, and that mathematical objects represent or model some kind of alternative or other kinds of reality. Now, that's another kind of world, and I use, let's say, English or Bengala or any other human language to talk about the experiences of the world around me, and I use mathematics as a way of explaining the phenomena of this other transcendental reality. And until I can teach you enough mathematics to teach you about that transcendental reality, I'm always stymied that I can't make you see that the beauty of mathematics. But you should know that it is there, and it is what drives mathematicians to do their work. It is what makes us mathematicians, and what gives us, as it were, the desire to study these abstract structures, because there is this language that we have that enables us to explore this abstract world. Yes?
If mathematics is a language, we know languages are plural and it has plurality and diversity in languages. There are different languages. There is not one language throughout the whole world. Mathematics is a language, but we see mathematics is the same language. 2 plus 2 is equal to 4 is equally true for all of the world. What is the linguistic, diversity and plurality in mathematics, if mathematics is a language?
If we had not evolved the way we evolved, that is to say, groups of people left Africa and moved around the world and so on, we would not necessarily have a plurality of language. Let's imagine an evolutionary story where humans all left Africa all at once, the tribe just upped and left, and they wandered over the Middle East, and then they decided that was boring, so they then moved further east, and they moved further east until all human beings arrived in Chittagong and decided this was the nicest place to live. So the human race consisted of the city of Chittagong and the farms around Chittagong, and there would be one language.
But people are scattered throughout the earth, in the whole planet, in the livable places. So they have developed different languages.
Yes, but my point is that that's coincidental.
Mathematics as well, from the ancient period to this day. But mathematical language is all the same.
Well, no, they're not.
In that sense, I think we can say that mathematics is more than a language. It is a language of science. That your language has restrictions. You can contact only with Bengali in Bangla. You can contact with English person if you know the English language. But mathematics has a universality in the content.
Yeah, but so that's his question. That's his question, is why this has occurred.
Unique. And he has given an explanation that if people would not have, scattered throughout the planet, and they would be in a specific place, they would have, one single language, then mathematics, something like mathematics. But the reality is that people are scattered, they have different languages and there are linguistic diversities.
If you'll allow me, I'm going to suggest you do have different kinds of mathematics.
Sorry?
If you'll allow me, I'm going to suggest that we do have different languages of mathematics. There are different ones. Because if you look, for example, at ancient Babylonian mathematics, it talks in a very different way.
No, this is the development.
Can I talk? I mean, if I may, I'd like to answer your question. You've posed something.
Please.
I mean, so I'd like to respond. So, for example, Babylonian mathematics is quite different from other forms of mathematics. More interestingly, when the Chinese first developed mathematics in the 2nd, 3rd century BC, what they developed was actually quite different from other traditions of mathematics. Now, you're then going to say, but I can map from anything the Babylonians say onto, for example, our mathematics today, which is correct. But I can map from Bengala to English. So I can talk about, as it were, this box of tissues in Bengala, and I can talk about it in English, and I can talk about it in Greek, and I have a mapping called a dictionary that will show me that what these words mean in one language and another. And I can look at Babylonian mathematics, or I can look at ancient Chinese mathematics, and it's a very different way of doing things. It's a very different mathematical language, but there's a mapping from theirs to ours.
And it's the same.
And the problem is that there is only one language of mathematics, but not a problem. The beauty is that today there is only one language of mathematics because, of course, a particular tradition has come to dominate mathematics. But that's a historical accident. You may want to call it colonialism. I wouldn't call it colonialism. I think that's a crude. It's a crude weapon to use to just say, "Oh, this is Western colonialism." That's not good enough. I mean, that's good for crowds out there, but if you want to, try and be a little bit more sophisticated, it's not colonialism. But it is certainly the case that there exists only one kind of science today. There is only one kind of mathematics. But I can look at Babylonian mathematics and I can map it onto our mathematics. Although when
if you map these two mathematics, they're the same.
Well, yes and no. Because, for example, and now you're on my territory, because this is history. This is how you do and don't do history. Because, for example, I can look at Babylonian mathematics, and it's really easy to translate it into algebra. And there are many people who say, I mean, bad historians, if I may insult my colleagues, there are many bad historians who will say, yes, the Babylonians had algebra, because here are the marks they made in clay, and I can describe these marks as the following algebraic equation. But they didn't have that algebraic equation, and there is an immense amount of knowledge and concepts in an algebraic equation. Most of you have never thought about this before, so that's okay. When you were at school and you learned algebra, you actually learned about equations in two different ways. Because the teacher would go up to the board and say, 2 plus 3 equals, and then would draw a blank space or put an underline. And that equals sign means do this computation. It's not equals, it says compute. So I will compute 2 plus 3, and if you were me at school, you would write down 7, because I wasn't very good at maths early on at school. So you do the computation. But then I say 2x plus 2 equals 10. Now that's a very different meaning to the equal sign, because that isn't the instruction to compute. That says something which is awesomely profound, which is that the stuff on the left, 2x plus 2, is true for a certain value of x when it equals 10. That's the equal sign, not as an instruction to compute, but a balance. And I will now play around with the things on the left until, and indeed the things on the right, until I get to, in this case x equals 4, I get the answer where when x equals 4, then 2x plus 2 equals 10 is a true statement. There's a huge amount of ideology, of interpretation in that sense of the equal sign. And that's, I'm always telling my undergraduates, you guys never think about this, but that idea of equality, that mathematical idea of equality, is one of the deepest ideas human beings have ever had, because you're saying the stuff on the left can be made equal to the stuff on the right. But when I look at it, I see a 2, an x, a plus sign, whatever I said, 2, and then on the right I've got 10. And those are profoundly different things. They're not equal. But I'm saying, well, at some level, in some interpretation, they are equal. Now, when I look at how an ancient Babylonian thinks, I need to see, if I'm going to say they have the equation 2 times an unknown plus 2 is 10, I have to look at that and say, are they thinking algebraically? Do they actually have this notion of equality? Do they actually manipulate this equation as a balance? And interestingly enough, they don't.
No.
They don't do that. I can interpret what they do in algebraic language, but that's not what they are doing. They are manipulating this in a different way. I'll give you another example, which is a classic example of bad history. That people look at the way Archimedes solves certain problems of finding area, where he will divide up the area into what appears to be an infinite number of infinitely thin slices. And then he says the sum of these infinite slices is, let's say, 5, or the area of this square. And people, bad historians of mathematics, will then look at this and say, so Archimedes was integrating because he summed up these infinite lines. Well, actually, that's not what Archimedes did. Archimedes said, I can divide this up into an infinite number of lines, and I say the area of the sum of these infinite lines is 5. How do I prove it? Well, he says, I prove it by saying, suppose not. So if the area isn't equal to 5, the area is either greater than 5 or less than 5. And then he will show that if you suppose the area is greater than 5, it leads to a contradiction. If you show the area is less than 5, it leads to a contradiction. Therefore, the area is equal to 5. Where did he sum up the lines? He never does. He doesn't integrate, because he knows he can't sum up an infinite sequence of lines. So Archimedes develops this is the Eudoxus' method of exhaustion, if you know about these things. And Archimedes actually doesn't integrate. He very explicitly does not sum up those lines. He says, if those lines were summed, they would have this answer, and I'll prove it to you by showing you that not holding this answer gives rise to a contradiction. So he proves it by recourse to logic, the law of excluded middle, rather than actually summing up the lines. So since integration does, in fact, precisely give you a way of summing up the lines, he very precisely doesn't integrate. And it's really easy to read Archimedes through modern eyes and say, look, he's divided into an infinite number of lines, the guy is summing them up, he's doing integration. And that's precisely what he doesn't do. So you can...
But it was the, linguistic diversity and plurality and mathematical linguistic uniqueness.
Well, but it isn't unique. And that's my point, is that when you get very close to what they're doing, you can see that actually Archimedes is doing something different from what we call integration. And the use of the word integration is false here. Like with the Babylonians, what they are doing when they solve arithmetic problems is in fact not algebra, it is algebraic recipes. So now, but the problem here is that all human emotion can be spoken about in Bengali, and all human emotion can be spoken about in English. So I have here two incredibly sophisticated languages that cover everything, whereas here I have to look at a primitive language because there is only one sophisticated language of mathematics, which is, as it were, that which has grown from the ancient Greeks. And if you will, the irony of history, and it's easy for me as a Westerner to say this, of course, is that the Western story of mathematics has become the universal story of mathematics. But in the 13th century, I had a story of mathematics, a language of mathematics in, let's say, Europe, but if I went to China, I had a different language of mathematics. I can map between the two of them. So anything I can do, well, roughly anything that I can do in the Western tradition, which is above all based on proof, and above all has the distinction between geometry and algebra very deeply embedded in its thinking. The Chinese don't distinguish in the way that we did between algebra and geometry. They don't see that as this kind of chasm of two different ways of describing things. So early Chinese mathematics doesn't make this distinction, so it is quite different in its concepts and its behavior. And of course, by the 16th century, the Chinese way of doing mathematics begins to disappear because it just can't compete with that which descends from the ancient Greek. Now, I don't want to get into the colonialism argument here, because I think it's inappropriate. But what has happened is that I think we are in part fooled by the universality of mathematics, by not seeing that there can be alternate mathematics. What saves it is, I can say this is blue in English, and you can say it is, well, what color would you call this in Bengali? Neri. Okay, so you have a different word. And I can map between the two, just as I can map in between two forms of mathematics. But they all refer to the same object.
Yeah.
And now you want to, your next question should take us to Kant and the existence of the transcendental object. And now we're in difficulty. And indeed, the rest of you don't need to know about this, okay? You don't want to go to Kant, don't go there, as well, you will lose your soul. But you and I know then, if we start to argue about mathematical objects as transcendental objects, or physical objects as transcendental, we now get into a real...
Are you a Platonist?
Yes, of course I am. I'm a mathematician, yes.
You think that numbers are abstract entities?
Sorry, that numbers...
Numbers are abstract entities.
Numbers, well, now, can we make something very clear? Mathematics is not about numbers. Arithmetic plays the tiniest part in mathematics. It's such a trivial part. If I excluded numbers,
geometry,
but in geometry, yes.
Let's take a circle. The circle in our idea is the most perfect circle. The circle we draw is not so much perfect. So according to Plato, that very ideational, that transcendental circle is a real circle, and all the circles are expressions and phenomena of the circle. So my question is that how can we get the connection between that ideal geometry and the real figures that we see and draw?
Well, Plato had a very good Plato had a very good answer to that, which is the doctrine of amnesia and the division of the world soul. So Plato has, as it were, a physiological explanation for that. In the last few centuries, maybe 2 centuries, we have given up trying to find a physiological model to explain our ability to understand the realm of forms. So we've given up trying to answer that question.
Physiological or physical? Physiological.
Physiological, yes. Whereas Plato gives you a physiological answer, which is that we all have a small part of the world soul, and the world soul is that which can perceive the forms. So, as it were, he invents a mind-body link which will answer that problem.
Mathematical truths are third ring. Third area, not body, not mind, but something else.
Yes. That's what almost all mathematicians would say. That is what almost all mathematicians would say. And as I said, most mathematicians will try to avoid this argument because they don't want to talk to philosophers and they don't understand philosophers. But if you're very quiet and gentle about it, I mean, try just scratching his arm very gently, and what you'll find if you scratch his arm very gently so he doesn't run away, he's a Platonist, because he's a mathematician, so he knows that mathematicians talk about a kind of reality which is not this physical reality but another kind of reality. And this is I won't say universal because there are always some exceptions, but this is almost universal amongst mathematicians.
So how the universals get connected with the particulars?
Yes.
Suppose this is the particular and it has universal,
Yes, but the reason you perceive it to have mathematical properties is that you know those mathematical properties from...
Two different categories, universals and particulars.
Okay, now, what I'm not going to do here is have the traditional argument between the philosopher and the mathematician, because we all know, including mathematicians, that there are many arguments against Platonism. But then I will return and say, okay, what are the objects of mathematics? And I know that whatever answer you give, it will be open to criticism by other philosophers. So, because, as well, Plato and Aristotle tried to answer this question without success, and every philosopher ever since Plato and Aristotle have tried to answer this question without success. So, when you guys come up with a good answer that you can all agree to, I'm going to put this crudely, I'll bother to listen to you. Okay, but until you come up with a good answer to what is the object of mathematical knowledge, I'm not interested in, as a mathematician, I'm not interested in your criticisms because you don't have an answer to the problem. Mathematicians who know their philosophy know that Platonism is open to criticism, as every philosophical doctrine is open to criticism, okay? But mathematicians...
There cannot be any philosophical
position. But mathematicians need to get on with doing mathematics, because they're not philosophers, they're mathematicians. So, as it were, in the end, what I want to do is mathematics, not philosophy. So mathematicians have a complex set of ideas about the nature of what they talk about, which allows them to get on with mathematics. You're entirely correct to criticize it because Platonism is open to, Aristotle tore it to pieces. So you don't have to wait long, you wait 30 years, and you have devastating criticisms of Platonism, which Platonism can't answer. I mean, the whole doctrine of intermediaries is a fatal flaw in Platonism, so that's that. Platonism is, in one sense, dead by the time of Aristotle, because Aristotle's critique of it is devastating. But I still need to do mathematics. So this will work, this will do, and as I say, crudely put, until you guys find an answer, stop bothering us. Because give us a better answer that solves the problem of the nature of mathematical objects.
The answer is better from its own perspective.
So, well, I mean, this is the answer that works for mathematicians in the sense that it's simple. It allows us to answer students who ask, so what are you talking about? It gives us an answer to that. It lets us get through till dinner, which is what we want, and it gives us a basis for doing more mathematics. So there's as it were, a real reason for this retreat to Platonism. And genuinely, you will find most mathematicians won't want to argue about it with a philosopher. But when mathematicians talk to each other, and again, there's something I do occasionally, which is in the maths faculty in Cambridge, I will sort of put on my pith helmet and act like David Attenborough, exploring watching some animals. And I occasionally will actually sit there like an anthropologist and listen to mathematicians talk about mathematics. And it is fascinating, if you ever get the chance, to sit very quietly in a room where there are mathematicians talking to each other, where they don't know that you're a foreigner, you're an outsider, and listen to the way they talk about mathematics. And two things will emerge which will astonish you all if you ever get to actually experience this. First of all, you will be astonished at the Platonism of mathematics, because they all talk about this other reality, which they know about, and they know intimately about, and they, as it were, they deal with every day. So for them, this other kind of reality is very intensely knowable and present. And then if you listen to them talk about how their metaphysics, how they think the world works, how they think mathematics works, if you listen very carefully, the mathematicians are almost, at least in Cambridge, for example, they are almost all atheists. If you ask them, what is your religion? Atheists. If you ask them, what is your religion? They will almost all say, I'm an atheist. But then you listen to them talk about mathematics, and they talk about mathematics in using an extraordinarily religious language. Now, it isn't Christian or Jewish or Buddhist or Muslim. It isn't any particular denomination, but they will talk about the world in very religious terms. And I always roar with laughter.
Contradictory, these 2 points, one contradicts with the other.
Well, that's why I'm saying it. That's why this is the reason I have just given this anecdote. They all say they're atheists because they are atheist. That is to say, they do not believe in a particular God. So they're not Christian, they're not Buddhist, they're not Confucian, they're not Muslim. Okay, so they don't follow any kind of organized religion. But if you listen to them talk, the way they refer to nature and the universe, do you think the universe is rational? Well, okay, I'm not talking about politics.
I'm thinking about the philosophical idea.
But
in some respects, your words is correct, because you see that mathematical formulations, ideas, abstractness, everything has the limit to applications. With everything which mathematical forms are invented, they are thinking about implemented in the real life. But philosophical ideas may not be. This is the main response for it.
Yeah.
Okay. These talks are there are 2 points. They are mostly atheist. Your second point. They are mostly talking about something which is matter of the other world, something transcendental, not physically connected to them. So mathematics is reasonable in the sense it is rational.
So it is reasonable? I didn't understand that word.
Because
no, there's a word I don't understand. That mathematics is. What was the next word that you said? Mathematics
reasonable. But rational in the sense of reasonability.
Reasonable.
Oh, reasonable. Sorry, I'm just simply not understanding your word. It is reasonable.
It's going about the
Yeah.
reality reasonable.
So,
Yeah,
it's rational in the sense of it is, in the sense that it is reasonable.
Yeah. But
When you talk about infinity, we cannot amount it, but we have an idea what is that.
okay, I'm sorry, I'm not following your point.
The point is that mathematics.
Sorry, I'm very sorry. I'm so full of this throat. I find it terribly difficult to understand other people just because. So speak again. No, I want to hear what he's saying.
we can discuss.
Okay, well, no.
Let's carry on.
No, actually, I had come to the end of what I was saying here, and I want to turn it over to you. Are there of what you would like me to discuss further? Not philosophy, because I'm not competent to talk. I mean, we have a philosopher here who can talk about philosophy. I can't talk about philosophy. But my point only is, much to the chagrin of philosophers, is that mathematicians almost all take a Platonist position. And that's something you notice through the last 2,000 years, is that mathematicians, now, philosophers know that Platonism is deeply problematic from the point of view of philosophy. So every philosopher immediately jumps up, as my friend here has just done, to say, but hang on, that's a contradiction. No thanks. And, that's a contradiction, that doesn't work, that's inadequate, and so on, which is all entirely correct. But mathematicians aren't philosophers. Mathematicians want to do mathematics. So we have here an answer to the question, what is the nature of mathematical entities? We take this Platonic view, and my challenge to the philosopher is, well, if you don't like our Platonism, then give us a good answer as to what the nature of mathematical entities is. And noticeably, philosophers have come to no answer to that over the last 2,500 years. And I always would then say, if Plato and Aristotle didn't solve the problem, then either they've misunderstood the problem, or there is no solution to the problem. And that is to say, Plato and Aristotle they both came up with an answer as to what is the ultimate nature of mathematical entities, and those answers are inadequate. They're open to criticism. So, as it were, they didn't succeed. I doubt I'm going to succeed. If Plato and Aristotle couldn't do it, guess what? I'm not going to say I can. And no other philosopher has done so ever since. So this is a genuine, active problem from the point of view of philosophers, but also from the point of view of mathematicians, that there is a disjunct, if you will, between that we do mathematics with extraordinary success, and even, if you will, the added miracle that this mathematics can be applied to the physical world, which is something that is even more remarkable, and something that actually philosophers don't talk about. And is a great pity that philosophers don't talk about, because that's a real mystery. Why is it that physics happens to work using mathematics? And indeed chemistry happens to work with mathematics. And I can tell you, in the last 10 years, more and more mathematicians are moving into biology, not to do statistics, but to do mathematics. Because it turns out biology can be mathematized. And I always laugh at my friends who do biology, who did biology because they were no good at maths. Because I always say to them, you're dinosaurs. Because now biology is becoming another mathematical science, and you're going to have to do mathematics in order to do biology. So the biologists who don't do maths, they're going to disappear in a generation or two, because mathematics is becoming very, very high-level mathematics. I mean, not just arithmetic or statistics, but very intensely sophisticated mathematics. There has been, over the last 50 years, and the last 2,000 years, the most extraordinary imperialism of mathematics in the other sciences, as mathematics has taken over science after science after science. But again, there's a reason for that, and this goes back to the ancient Greeks, and that is that the ancient Greeks, when they started to do philosophy, and that includes science or natural philosophy, when the ancient Greeks started to do this, they got this lovely idea that you could gain knowledge of the world. If you could just kill it. If you could, with the project of the early natural philosophers was that you could gain knowledge of the world through reason. And this is the Greeks are starting to talk about this by about 500 BC. And this is a very sexy new idea that I can find out about the world by thinking about it and reasoning about it. And this is where Parmenides comes along about 480, 470, so only a generation later. And Parmenides comes along and, as we're developing the most extraordinary rational skepticism, he devastates the original project of natural philosophy. This is Parmenides' long poem, which is usually given the title On Nature. That title is much later. The original poem was something like 700 verses long. It's an enormous work, of which we have fragments of about 130 verses, and we have complete verses from only about 50. So we don't know much of the argument, but there are enough fragments from later and commentators on it that Parmenides argues that the use of reason gives rise to ridiculous conclusions. And he shows you a reasoned argument where, starting from reasons where I would say, well, you agree that this, and you would agree that, yes, we all agree to that. And then from this to the next thing, he will argue, so therefore this, so therefore this. So by reason, Parmenides arrives at the conclusion that there is only one thing in the universe, one thing, and it cannot be divided, and it cannot be changed, and there is no motion or multiplicity in the universe. So there are not two things in the universe. And I show you my bottle and its cap, and I show you therefore that I can see there are two things in the universe. And Parmenides' point here was, yes, that's why the use of reason is so stupid, because your use of reason takes you to the ridiculous conclusion that there is only one thing in the universe. I can argue to that, as it were, deductively, and we know that there's a multiplicity of things in the universe. Parmenides is not arguing that there is only one thing in the universe. He's saying how stupid the philosophers are to use reason to gain knowledge of the universe, because it arrives at ridiculous conclusions like this. So Parmenides invents radical reasoned skepticism, using reason to criticize reasoned arguments. And it's absolutely devastating. After Parmenides, after, let's say, 470 BC, if you want to do science, you have to answer Parmenides. And indeed, all subsequent science always begins somewhere at its foundations with an answer to Parmenides. How can you have knowledge of the world? How can you be in a changing world and have knowledge that is unchanging of a changing world? And that's what science does to this day. We have this thing called scientific laws, which we hope are unchanging, in theory, are unchanging, and those scientific laws are the unchanging regularities that the physical universe has or possesses. And the first thing a philosopher then should ask is, in what way can an object possess its laws? My favorite example of this is to hold up a pencil and let it drop and say to a room full of physicists, why does this pencil drop? And don't say gravity, because that's a word, that doesn't explain everything. So the physicists will start to, they'll faff around the place and they'll talk about this and that and so on. And somebody eventually will say, the pencil feels the pull or the attraction of the center of the earth, or the mutual attraction of two bodies, which is what I'm waiting for. So I'm saying, okay, so this pencil feels. This pencil has a soul and is animate and feels, and this pencil feels the call of gravity. I feel the center of the earth. On a sunny day, I feel this beautiful center of the earth, and I feel the pull of. My pencil doesn't feel anything. It's inert.
Yeah, not at all.
But we describe it as feeling. And this is not just a joke. In what way does an object feel the laws of physics? It manifests the laws of physics, but without giving the object some kind of cognate, sensate soul, how does it feel the laws of physics? Here's a law of physics, and this object obeys the law of physics. Well, I have to be, as it were, an intelligent being, or at least have some kind of intelligence to obey the laws of physics. Our language here is exceedingly dangerous. And this is a philosophical problem, or on the other hand, a problem of physics, which is not easy to explain, is in what way can these manifest laws be seen to be imbued in the inert activity, the unsouled, uncognizant activity of inert matter. That's a problem. Physicists and philosophers, in effect, call it the mind. Well, it comes down to the mind-body problem. And since Descartes, that has been a catastrophic problem at the basis of all physics. All science has this problem of the mind-body. How do we activate inert matter? And I mean, again, physicists don't like to answer this question because or don't like to talk about this because they don't have a good answer to the question.
So gravitation is not a good answer.
Sorry?
Gravitational force is pulling the stone on the ground.
Well,
it's not.
I can give you a great deal more physics than gravitational forces. Okay, I can give you a huge amount more physics. I can bend space and time. I can give you a large amount more physics. But in the end, we always come to something which is an inadequate answer. Always. There is no if the physicists. I mean, watch these guys. If the physicists ever do discover the final answer, all the rest of us are out of work.
All the rest of us?
Are out of work.
Oh, yes.
There'll be nothing further to do. In which case, what we have to do is shoot the physicists so that they never find the final answer, the complete solution to everything. And the physicists are aware of this, so they know if any of them do find the complete answer to everything, they know to shoot that person because we must not have. So, I mean, joking apart, there is no final answer. Oh, well, if you will, the final answer is religion. When you attribute everything to some supernatural power or some supernatural force.
We say nature.
But, exactly, we use the word nature instead, which is equally inadequate. It looks to me like you all should be eating. So,
please continue.
No, I'm actually. I've had a breakfast and I've had a snack as well, so I'm fine.
Please continue.
So, okay. I mean, if you're happy to continue.
One question, please.
Yes.
Mathematics, science.
Is mathematics a science? Now, I have this argument all the time, and I cannot understand why it's a problem.
Peculiar question.
Yeah, I cannot understand why it's a problem.
It's not mathematics, but they are telling is mathematics. It's science.
Because
Tools of science.
They are
although
solving everything by mathematics. Just now, question is that is mathematics.
but the answer is very simple.
Just like your last paragraph.
The answer is very simple, because mathematics uses a different methodology from science. Mathematics doesn't do experiments. So it has a different methodology. But the methodology of science, experiment, is subject to one universal limitation. It must be independently rediscoverable. If I do an experiment and I find that, whatever, find something, if I do it, you have to be able to do the same experiment and get the same result. The independent rediscoverability of science is its absolute core criterion. Only Beethoven could write a Beethoven sonata, but anything you do in science must be doable by everybody else. If it isn't science. And that's, as well, there's no rule more fundamental than that in science. And of course the whole point about mathematical proof is that when I have a mathematical proof, everybody else can follow that proof. That proof is inviolate and unchangeable and independently rediscoverable. So there's an epistemic bar, an epistemological bar in science, which is independent rediscoverability. And it is absolute. If it is not independently rediscoverable, it's not science. End of discussion. So therefore, mathematics has the same, it has a different methodology, but it has the same epistemic bar. It has to be independently rediscoverable, so it is a science. It doesn't do experiment, that's all. But as well, that's just a nuance in methodology. The epistemological status of the laws of science and the laws of mathematics is always the same because it's independently rediscoverable. Yeah?
The central issue of discussion here is mathematics as a language. So I have a comment over this. I think mathematics is a language that complements traditional languages.
Yes, I mean that's certainly true.
Let me explain what I mean. If we have a thing called pendulum and it is moving, if we want to describe its motion, where the motion velocity will be maximum, where the acceleration will be maximum. If we want to describe it in English or Bengali, we need 1 pages, 2 pages, 3 pages. But still, there will be something untold. But if we describe it in a equation, differential equation, then all its physical phenomenon, all its meaning will be told in a simple language.
Hold on though. I can go beyond physical reality in mathematics. Mathematics is not limited to physical reality. I mean,
but it is one of the examples.
Well, but what about when I talk about, you know, a p-adic algebra, which doesn't exist anywhere in physical reality?
Which is that, sorry?
I just pulled out a p-adic algebra, p-adic. It's a kind of algebra, but it's a kind of algebra which you don't encounter in physical reality. So, what is that a description of?
It describes something. This is a language.
Okay, but what is that thing that it describes?
It describes some phenomenon or physics or something.
No, the point is I'm talking about something that's not physics. No, see, I want to make it a very clear distinction that you're saying that language, like with the pendulum, is an addendum to ordinary language, and I certainly see exactly that point. With a pendulum, the mathematics adds to, it is an addendum to the physical phenomenon that we see. But that's not really what mathematics is about. Mathematics might well describe a pendulum accidentally, that's fine, but that's not really what mathematics is about. Mathematics is about abstract structures which are not necessarily extant in the physical world. So I can talk about something for which you have no physics. So now can you say that mathematics is an addendum to English? Because I can't describe a p-adic algebra in English, because English uses words that model our experience, like a pendulum. That's why you can do it. But I'm now choosing an example which is exactly not like the pendulum, because you have no experience of a p-adic algebra in your physical, in the physical world. So you have no words in English which can talk about it, which is why it begins to become a description, if you will, a geography of something which English can't describe, because it is experiences that you can't have. And this always goes back to your point, and as we're still talking to you, in a sense, because you asked the most important question of all, which is, so what is this thing that we keep talking about, this mathematical beauty? And I keep saying, I can't tell you what it is, because...
But you feel it, and we can also get it intuitively. Well,
you can, if I tell you it's exquisite like music or sex, because I want to say that those two have a beauty, and they're very different kinds of beauty, or ecstasy, then at least you know that you've experienced the beauty of a painting, you've experienced the beauty of sex, I hope. So you've had some experience there, and you can say, okay, well they're talking about something which is like this. I know that's a good start to know what it is that mathematicians enjoy. But I can't show you that beauty unless you do the mathematics. And this is where I am robbed of my physical roots. Whereas I can talk about the pendulum, because you and I have experienced a pendulum. And if you talk about weight or space or time, you and I have those terms in our English vocabulary. So that's where you're absolutely correct. Mathematics becomes an addendum to English, because it adds to.
That is what I am saying.
But that's almost accidental in mathematics, because mathematics is not about pendula. Mathematics is about abstract structures which most of the time have no physical representation, have no physical meaning. In a sense, the miracle, which none of us, neither the mathematicians nor the philosophers nor the physicists understand, the miracle in this is that actually quite regularly we find that the world, the material physical world, appears to work according to mathematics. And, that's weird. When we discover that leaves, if you look down a branch at the way leaves stick out, sometimes they stick out horizontally, sometimes they're opposed to each other, but quite frequently they rotate according to the Fibonacci sequence. And you can either say, so God has a really good sense of humor and put a Fibonacci sequence in there, or you say, well, nature thinks in terms of Fibonacci sequences, and nature thinks, what do you mean by those terms? I mean, that has no good meaning. So why does nature in some way choose a Fibonacci sequence here? This is weird, and we don't have a good answer to these. I mean, we may do in this case, but we don't in general have a good answer as to why nature chooses to obey mathematical laws. And every time I talk about this, do you notice I use animate terms? I said nature chooses. I've just imparted to nature a consciousness that nature chooses. And doesn't make choices.
Not without any subjectivity.
Yeah, so nature doesn't choose, but we use this language of nature chooses. Because we don't have any other terminology to use here. And physicists have been banging their heads against the wall about this, about the way that we always seem to impart teleology to nature, that nature works as if it has a mind and a purpose. And physicists know perfectly well that nature is not teleological. But we always talk about it teleologically. Do you want to take a break? I mean, I'm sitting on a cushion. You're sitting on hard chairs. So my bum is not numb. Yours must be in pain. So I mean, I'm happy to keep talking.
Please, I have a question. You are saying that mathematics transcends the physical reality.
Yeah.
If there is a contradiction between common sense and mathematical reality, suppose, then how could we solve?
Well, now let's go back. Let's go back to Karl Popper, which you did in your little paper there. Let's go back to Karl Popper and ask the question, is mathematics falsifiable by an experiment? And then I'll give you the very simple example. I claim 2 + 2 = 4. So if I have 2 liters of water and 2 liters of water and I mix them, I get 4 liters of water. That's obvious. If I take 2 liters of water and 2 liters of alcohol, I get about 3.6 liters of mix, because alcohol dissolves into water. So, let's do this experiment, and I see that 2 liters plus 2 liters equals 3.8. Have I falsified arithmetic, or have I explained this phenomena by recourse to chemistry? That is to say that one liquid dissolves in another liquid.
This is a common sense question. Yes.
Well, I don't know if it's a common sense question. I don't know what you mean by common sense here, and I'm very suspicious of what common sense means here. But I've done this experiment, but do you notice it doesn't falsify arithmetic? We didn't all do this experiment and then go, oh no, arithmetic is wrong. We've been playing around with arithmetic all these years and it doesn't work. Damn. We're going to have to go back to the blackboard and find something that does work, because arithmetic, I've done an experiment and arithmetic has turned out to be false. No, we say that this is not an arithmetic phenomenon because water dissolves, alcohol dissolves in water. So we don't falsify mathematics through physical experiments. So it's not falsifiable. It's not falsifiable using experiments. It's falsifiable by other means, the proof, the idea of proof. So proof is the methodology through which we test and falsify. We open to falsifiability the ideas of mathematics, and, if you will, experiment, crudely put, is the way in which we falsify, or we make falsifiable, claims of science. Now, neither of those are true. Okay, both of those are absurd overgeneralizations. But at the level of school children, you can tell that to school children. Because, of course, proof and rigor change with time, and what you regard as a failed experiment or a falsifiable experiment changes with time and social context. So neither of these are as absolute as we like to claim they are. It's more complicated than that. But as a childish generalization, you can say that mathematics is not falsifiable by its lack of application to the physical world. And I can give you, what did I say? I said a 5-dimensional knot in a 9-dimensional space, and you can't physically verify that, because you can't have a 5-dimensional, I mean, we can't make them. I mean, maybe they can be made, but you and I can't. If you know about string theory, you know that string theory sometimes talks about, you know, there being 29 dimensions, or whatever today's flavor is, 17 dimensions, and so on. And these dimensions are curled in on themselves and so on. I'm always sitting down with my colleagues at lunch and going with the string theorists and going, experiments, gentlemen, experiments, because they have no experiments. Because they're doing mathematics, but they can't do any experiments. And until they can do experiments, this is theoretical physics. It's not physics, because the experiments are the option of falsifiability. So if I'm making a claim, it has to, in physics, it has to be falsifiable by experiment. And only when it's falsifiable does it have physical meaning. In mathematics, if I make a claim, that claim has to be provable. And only when it's provable, when it has been proved, do we then say, okay, it's passed the test, we now know this to be true. So that's why, as it were, the common sense argument here fails, although the common sense argument is a perfectly good way to live life, as it were, to be a human being. So I'm not going to disagree with you there.
Can we improve the common sense with this, greater realities, instead of cancelling the common sense?
I would go back to show me a 5-dimensional shoestring in 9-dimensional space. And this doesn't exist. So that's why what the string theorists doing is maybe good mathematics, but it is not yet good physics, because they can't test it with a physical experiment. I'm not claiming as a mathematician that there exists in the physical world a 5-dimensional shoestring tying knots in 9-dimensional space. I'm claiming that this is a consistent and intelligible belief to have, and you can have sure and certain and timeless knowledge about it in mathematics. But I don't claim that those things exist in the material world. And I come back to it, the extraordinary thing is that we attribute to physical phenomena mathematical properties. And I don't think anyone can explain to us why. And to me that seems to be the core miracle, the core thing that we don't understand.
So how mathematics became superior?
Okay. Thank you. That is the next question, because I will give you 2 answers. One quickly, and then if you want to have a break, or I'll just continue on to the second session where I'm going to talk about the scientific revolution, Renaissance and scientific revolution. But the answer, I was talking about Parmenides a minute ago, and I said that there is this extraordinary moment. The philosophers, the Greek rationalists, start to say we can talk about the world, nature, roughly. We can talk about that using reason. And then Parmenides comes along and says, yeah, and your reason takes you to ridiculous conclusions you know are not true. So at this point you have to answer Parmenides. And one of the ways in which the ancient Greeks immediately begin to answer Parmenides is the most extraordinary intuition. This has happened by about 450 BC. So we have the Greeks talking about philosophy of gaining true knowledge through reason around 500 BC. By 470 BC, so 20, 30 years later, we have this attack on the pretensions of the rationalists from Parmenides. And 20 or 30 years later, after that, we find the first answers to Parmenides, which are for the philosophers to start to say, to go over to the mathematicians and say, well, the mathematicians seem to be very sure of themselves. So there's a basis in sure and certain truth. At this point, obviously what happens is that the skeptics, who are Parmenides' pupils, like Zeno, you've heard of Zeno's paradoxes, the skeptics, the rational skeptics like Zeno, begin to turn on mathematics and start to criticize mathematics. And this is where the Greeks develop early ideas of reasoning in mathematics to an explicit theory of proof. And between 450 BC and 430 BC, I can't identify it to any less of a time than that generation, but in that sort of 20 years, they develop what we today call proof. It's a very simple version of proof, but it's a proof. And it is this idea that a geometric claim is true and necessarily true if I can construct it using only a ruler and compass. Nothing else. I can't measure anything, I can't make any proportions, I can only construct it using a ruler and circle. And this allows them to construct all sorts of answers, solve all sorts of problems, and say, I know this to be true because I have constructed it only with ruler and compass. This will get strengthened in 200 years' time by Euclid, who then shows all of mathematics can be derived from a very small set of first principles. We talk about Euclid's 5 axioms. Actually, there are about 20 axioms in Euclid. And what you've been told are Euclid's axioms are not actually his axioms, but never mind. He says, let's start off with a bunch of very obvious things that can't not be true. For example, if A equals B and B equals C, A equals C. It's quite hard to imagine a universe in which that's not true. It's really quite hard to imagine that. I can't hear you.
It's logical. It's applying logic.
It isn't applying logic. It's establishing the meaning of equality. If A and B are the same, and B and C are the same, then A and C have to be the same. So it's even more primitive than logic. It's what you mean by equality. And he begins with this number of first principles, and then shows that from those first principles, you can, using ruler and construction only, ruler and circle construction only, you can construct the rest of geometry. Now, Euclid's axiomatics make geometry impervious to skeptical attack. And indeed, we find after Euclid, the rational skeptics of the ancient Greeks who will attack anything, any place. They will use reason to criticize any other reasoning, and they're enthusiastic and brilliant at it, but they stop attacking mathematics, because mathematics, with axiomatics, mathematics becomes impervious to skeptical attack. And that's the first place where mathematics becomes seen as the primary, the highest, if you will, of the pyramid of sciences, is that from about 450, people recognize mathematics as being the paradigm of truth. What we mean by true is things are true like mathematics is true. That actually becomes, that's the meaning. And you ask Plato, or ask Aristotle, what do you mean by true? And he'll give you a long chatter, but in the end he says, so true is what true is the state of certainty that mathematicians have. And pretty much ever since, all philosophy of science has eventually come back to, yeah, it's true because it's like mathematics, and mathematics is our paradigm of truth. And what we don't tell you is that mathematicians don't know what true means. After two theorems of Kurt Gödel in the early 1930s, we no longer have a meaningful use of truth in mathematics. But we don't tell the general public that, because we wouldn't want you to think that mathematics isn't true. But in fact, in the last century, we have come to understand that the term truth doesn't have a good meaning in mathematics. Yet, sadly, everyone takes truth to be absolute in mathematics. So, that's the first step in this, in the way in which mathematics has become the, I don't want to say the highest science, because I don't think it is the highest science, but they were the top of an apex where you have, maths and then physics and biology and so on and so forth, and you get down to lawyers and protoplasmic sludge at the bottom. Or I should say lawyers, and then at the very bottom, politicians.
Imperialism.
Sorry?
You told him imperialism.
Yeah, but ultimately, yeah. So that there is this idea of this pyramid of that mathematics is the most certain. Now, I was in my second session going to not talk about ancient Greeks. I'm very happy to talk about the ancient Greeks if you'd like to carry on talking about the ancient Greeks. But I was going to talk about the Renaissance and the scientific revolution. And in a sense, I wanted to answer your question, which is, why does mathematics, what is it that gives mathematics the status that it has today? Because whilst the Greeks regarded mathematics as epistemically supreme, it was the most certain of their sciences, the Greeks did not think that the world in general, in general, the Greeks did not think that the world was particularly mathematical. Now, Plato thinks the world is mathematical. Aristotle was much more cautious and said, yeah, some things are mathematical, a few things are mathematical, but most things are not mathematical. Most things cannot be known about using mathematics. And Aristotle would give the very simple example, here's a chair. Now we all know it's a chair, you can tell it's a chair, and it has the use of a chair. And I'm going to measure this distance, and it is, let's say, 32.3 centimeters. Now if it was 32.4 centimeters, so if I change this mathematical value, would it cease to be a chair? No, it's still a chair. Okay, how about 33.5 centimeters? Still a chair. What about 2.2 kilometers? No, it's no longer a chair. It's, I don't know, a building, something else. But it's not a chair. Ah, says Aristotle. So a thing, a chair, does not hold its quantities as part of its necessary properties. It holds the quality of those quantities. So the quality has to be kind of small, like between 20 and 40 centimeters, that sort of thing, and then it's a chair. But if it gets much more than 40 centimeters, then it's not a chair, it's something else. So Aristotle notes that it is the quality of the quantity, not the quantity itself, that makes this a chair. And similarly for geometric things, for flatness and so on. If something is roughly flat, it does the job of something that's flat. But if it isn't perfectly flat, it's just roughly flat. So Aristotle draws the conclusion that most things hold their mathematical properties as an accident rather than part of their nature. He notices there are some exceptions. And the three exceptions he talks about are music, that is to say harmonics, and optics, because because light travels in straight lines, or astronomy, because astronomy appears, the movement of the heavens, the planets and the stars, appears to be exactly and eternally geometrical. And Aristotle has a reasonably good argument as to why astronomy should be both, shall we say, physical and mathematical. Here's a physical thing that can hold its mathematical properties essentially. He's got a fairly good argument for that. He's got a not very good argument for harmonics, but it's rough and ready, it'll do. And he has no argument, sorry, I said that the wrong way around. He has a rough and ready argument for harmonics, but he does not have a good argument for optics. He really can't explain why optics uses mathematics. So, but he can, it's the kind of thing in science all the time. You have unsolved problems and you leave them for graduate students to solve. So he's not overly perturbed by this. So Aristotle can make this distinction between these three sciences where you can use mathematics and physics, and most of the other sciences where, frankly, mathematics doesn't tell you much about things. And Aristotelian thinking will become the dominant thinking in the ancient world. It will become the dominant scientific thinking in the early medieval Muslim world, and it will become the dominant thinking in the Western medieval world. So this kind of slightly, mathematics has its uses, and mathematics is certain, but mathematics isn't terribly useful in, let me call it physics, or the physical sciences. This view becomes kind of the common view after Aristotle, and is the view in both Islamic and Christian scientific endeavors. And then in the Renaissance, this all changes, and changes completely and radically. And one of the upshots of the scientific revolution is very simply that mathematics becomes the core science. And with Newton and after Newton, when you do science, basically you do maths. And everything else is just the add-ons to mathematics. So I ask your question, how does mathematics become so central to science? And what was the process by which people came to see that mathematics is in fact, or is a useful way of understanding the universe? And as it were, this is a story where they come to the right answer for the wrong reason. And it's the story of science in the Renaissance. And many of you may have read histories of science, And one of the things that histories of science will tell you is that during the Renaissance, there was extremely little new science done. And that's one of the dogmas about the Renaissance, is that science is in the doldrums. And the only thing that's kind of interesting about Renaissance science is Copernicus and his introduction of the ideas of heliocentricity. And that's wrong too. And I'm going to explain that Copernicus did not, in fact, introduce heliocentricity. And in fact, if you read Copernicus's book, De Revolutionibus, published in 1543, you will discover that there are two models of the heavens in Copernicus, neither of which you think is correct. They're both wrong in terms of subsequent science. I don't know why you don't know this. I don't know why this is not widely understood. But there is not a Copernican model, there are two Copernican models, and they're both wrong. And as it were, you know they're both wrong, and people at the time knew that they were both wrong. And what Copernicus